So you can see that the title of my talk is To Fragment or Not to Fragment, Viability of Non-Contiguous OFDMA in Multi-Hop Networks. We all know that the demand for wireless is increasing rapidly. Qualcomm predicts a 1,000-fold increase by 2020. In order to meet this demand, FCC has opened up 300 megahertz bandwidth in TV bands, and FCC also plans to open up additional 500 megahertz licensed by rule channels by 2020. So by licensed by rule, it means that like any radio that abides by FCC rules might be able to use these channels. Now, if uncoordinated networks use these channels, then they will adjust spectrum usage according to their own traffic demands. As a result, the available bands will become non-contiguous and fragmented. For some bands, like TV white space, the available channels are itself non-contiguous in nature. Now, how can we access these non-contiguous spectrums or non-contiguous bands? And that's where non-contiguous OFDMA come into play. Now, let's look at this scenario. Here, node A is transmitting data to node C via node B. Node B is transmitting its own data directly to node C. There are three channels in the network, channel 1, 2, and 3. Node X is an external interferer and uncontrollable interferer, which is creating interference in channel 2. Now, if we have to if you have to allocate resources among node A and node B, among these three channels, and if we use the max mean rate objective, then node B is likely to get 2 channels, and node B is likely to get 1 channel, because node B has to carry node A's data. But then the question comes, which channels go to which nodes? Or in other words, the scheduling options for node A and node B. Now, there can be multiple options for this. One option is contiguous frequency division multiple access. Node A can use either channel 1 or channel 3, and node B can use the remaining 2 channels. Node B can do that using a single front-end radio, but it will suffer interference in in channel 2 in link BC. The second option, it's becoming a popular option in commercial chips, is that to use multiple RF front ends. That means node B will use 2 radio front ends. One front end will transmit channel 1, in other front end it will transmit in channel 3. Node A will use channel 2. So in this way, node B will not suffer from interference in link BC, but the number of spectrum fragmentation will be limited by the number of radio front ends. So when you get a radio, normally, since it will have a fixed number of parallel radio front ends, and in uncoordinated networks, sometimes you cannot predict the number of fragmented spectrum chunks that you will see. So that's where the third option comes into play, or non-contiguous OFDMA. Node B can use 1 radio front end, transmit in channel 1 and channel 3, and null channel 2, or put null subcarriers in that channel using NC-OFDMA, and node A can use channel 2. So how does node B do that? It's very conventional. So let's say node B is trying to use channel 1 and channel 3. The data for 1 and 3 are coming here, and after it goes to the serial to parallel block, node B puts 0 or nulls the subcarriers in channel 2. Now, there comes this new challenge. That means here in NC-OFDMA, node B is using 3 channels instead of 2. That means it's transmitting data in channel 1 and channel 3, but it's spanning 3 channels instead of 2. And if it uses a Nyquist sampling ADC or DSC, then the sampling rate increases due to the use of NC-OFDMA. So we can see that NC-OFDMA brings both benefits and challenges. It allows users to avoid interference and incumbent users. It allows radio nodes to use better channels, but it increases the sampling rate of the radio nodes. As a result, ADC and DSC power consumption increase, and amplifier power consumption increase too. So this figure, it shows power consumption versus sampling rate curve of 2 ADCs. The red one is the ADC model of USRP software-defined radio. The blue one is a ADC of Texas Instruments low power ADC group. So you can see that the slope varies from one curve to another, but they have a slope. That means If you use higher sampling rate, if you span more spectrum, then you'll consume more power in your ADC. So this just shows a typical radio transmitter and receiver path of a typical radio. So for example, in the transmitter path, the baseband signal is going through a DAC, then it's going through filter, local oscillators, programmable amplifier, and reaching the antenna. The receiver front end is working in the opposite direction. Now, among these blocks, apart from DAC and ADC, all the other blocks deal with analog signals. So their power consumption do not depend on sampling rate in general. Programmable amplifiers power consumption is slightly dependent on it is dependent on sampling rate, but we'll talk about it later in our talk. But in general, the power consumption of the transmitter and the receiver path, it's an affine function of the sampling rate. So the constant terms come from these analog blocks, and the linearly varying term comes from DAC and ADC. So we represent the transmitter and receiver power like this. So here Fs is the sampling rate, Pm is the emitted power at channel M. So summation of Pm is the total emitted power that the transmitter is transmitting, and these are the circuit power consumption in the transmitter's blocks, and these are the receiver system power consumption in the receiver's blocks. And based on this power consumption model, we focus on minimizing system power in a multi-hop network subject to rate requirements. So I'll show a glimpse of the optimization problem here. I won't show the whole problem, but hopefully it will give a view of our approach. So in our optimization problem, we want to minimize the summation of the system power among all nodes in the network. So we have a multi-hop network, data is flowing through multiple paths, but we are trying to minimize the summation of system powers. So by system power, we mean the summation of transmitted power in radio frequency plus the circuit power consumptions in the radio front ends. So here you can see that the system power of each radio is coming from the transmitter circuit power consumption, the receiver path circuit power consumption, and the emitted power in radio frequency. We have other constraints like flow capacity constraints, which is very typical. Flow cannot exceed the capacity of a path. And we have interference, flow conservation, and half duplex constraints. So in this talk, I'll illustrate how this system power minimization approach gives you very different scheduling results than from transmit power minimization approach. So in a typical transmit power minimization approach, which I will describe by the term water filling, it mostly focuses on minimizing the total transmitted power in the radio frequency. And it also has the same kind of constraints: flow capacity, interference, flow conservation, half duplex constraints. But in our case, the approach is different. We are trying to minimize the system power instead of just the transmitted power. So at first, let us look at an example and see how it works. So here we are looking at a point-to-point link. That means there is just one transmitter, one receiver. There are 20 channels. Each channel width is 3 megahertz, and minimum record rate is 18 megabits per second. Now, with this requirement, the water filling or transmit power minimization approach will allocate its resources in this way. That means it will select the good channels throughout the whole list. So if you look at the channel here, the link gain is given here. So you will see that there is actually one good channel between every 2 bad channel and one bad channel between every 2 good channels. So I guess created it through simulation. But if I run the water filling or transmit power minimization approach, it will select all the good channels and it will span the whole spectrum. But since it will span a large spectrum, the ADC and DAC power consumption will go up. But in our case, since our algorithm tries to minimize the summation of transmitted power and ADC and DAC power, it only selects the 2 best non-contiguous neighbors among this whole channel list. It puts more power in each of those channels, and then it meets the requirement. So this is how our algorithm performs or compares with a transmit power minimization approach. So this one is showing transmit power consumption curve, and this is a system power consumption curve. So you can see that the water filling consumes less transmit power than our case. So water filling does what it is intended to do. It uses less transmit power to meet the requirement, but it consumes more system power because it spans a wider amount of spectrum and it's consuming more power in ADC and DAC. So our approach reduces the system power by 4 dB here. Now let us look at a multi-hop scenario. Here we assume that there are 6 nodes. They are located in Wichita, Kansas. They are trying to use the TV bands to form a network among themselves. There are 2 sessions. Node 1 is transmitting to node 3. Node 4 is transmitting to node 6. And all of these are fixed devices. And using standard spectrum databases, I found the available channels in that city in TV bands. So these are the available channels. You can see the TV band indexes. You can see the carrier frequencies, center frequencies. So channel 2's frequency is 57. For example, channel 17 is 491. So you can see that the available channels are very fragmented from each other. Now, at first I will illustrate the scheduling decisions that the transmit power minimization based approach will take in this scenario. So this water filling approach, it selects these routing decisions, which will be same as our approach. That means node 1 will transmit to node 3 via node 2. Node 4 will transmit to node 6 via node 5. But let's see what are the scheduling decisions. So at first let's focus on link 12. So these are the channel gains across all these 7 channels in this particular link. So I got these channel gains from large fading and also from small fading. So I had a path loss exponent and then I assumed 10 dB variation among the channels. So these are the channel gains in this link. And water filling approach selected the best channels in this link because by default it is trying to minimize the transmit power. So it selects better channels in each link. So here the best 2 channels are channel 23 and 24. Water filling approach put these channels there. They turned out to be contiguous in this particular scenario. Now let's look at link 23. Here the best channels are, or the better channels are channel 2 and channel 17. So since water fillings or the objective was to minimize the summation of transmitter power, water filling selected these 2 channels in this link. In link 45, water filling again selected the better 2 channels, channel 5 and channel 17. Link 5-6, it selected channel 2 and channel 24. Now these channels probably helped your optimization problem in terms of minimizing transmitter power. But since the channels are very fragmented with each other, if you used a Nyquist sampling ADC or DAC, it will lead to consumption of a lot of power in your radio front ends. So our approach considers power consumption of those blocks and then performs its optimization problem. So here the top figure shows the ADC power consumption, which I showed before a few slides ago, of 2 commercial ADCs. The bottom figure shows DAC power consumption of 2 commercial ADCs. The curve with the higher slope comes from USRP DAC, and the curve with the lower slope comes from a Texas Instruments low power DAC. So at first we run our algorithm with the curve with the lower slopes. And these are the scheduling decisions that our approach takes. And you can see that our approach is selecting only contiguous channels almost in each line. So these channels might not be the best channels in each of these links, but our approach is selecting these channels because it is considering ADC and DAC power. And if you use a contiguous portion of the spectrum, you'll end up using less system power. So this is how our approach compares with the transmit power minimization based approach. So the transmit power minimization based approach, it requires less transmitter power, but obviously it requires more system power than our approach. So even here our approach reduces system power consumption by 4 dB. Now if I focus on the high slope curves, high slope ADC and DAC curves, that means ESRP's ADC and DAC, these are the scheduling decisions that our approach takes. That means here our approach selects only one channel in each of these links. So why is it selecting only one channel in each of the links? Because the slope is very high in each of these curves. So if it selects two channels, then it will have to use a lot of power in the ADC and DAC. So it makes more sense if you put more power, transmitter power in one channel instead of spreading your data in two channels and use more power in ADC and DAC. Now this is how our approach compares with water failing approach in this scenario. So you can see that if this type of ADC and DACs are used in real-time communications, and if a network designer uses water filling approach, that means only if a network designer only selects channels based on link quality, then the summation of like power consumption of those 6 nodes, the summation will be this huge amount. So that becomes impractical. So one has to consider the whether the available spectrum is fragmented or non-fragmented, and one has to consider the power consumption models of the ADC and DAC. So this is what we find in our work. Traditionally, there have been a lot of works that show that channel gains and traffic demands determine power control, scheduling, and routing variables. But our results reveal that hardware configuration of the radio front ends, for example, slope of ADC and DAC power consumption curves, can influence power control or scheduling decisions too. So in the future, we plan to model power consumption curves of programmable amplifier too, because that is nonlinear due to the bandwidth gain product. And we are also interested in investigating power consumption models of multi-front-end radios, and we plan to do it with the WINLAB CRT toolkit. Because if you have multiple radio front ends, then you can put each of your radio front end and make the center frequency in the fragmented chunks of the spectrum. In that way, you'll be able to reduce the digital power, since the ADC and DAC will span less amount of spectrum, but the analog power may increase since there are multiple analog components. So that's one area we plan to look ahead in the future. So that's all I had for today's talk.